So I want to walk you through how to interpret graphs, especially in this first unit with kinematics. We use graphs to represent lots of very interesting results. So I want to show you how to interpret graphs, but understand that this technique is important for all graphs, not just kinematics graphs. So we'll be revisiting this technique over and over again in every unit. So I want you to be able to make predictions about the motion of a system, whether it's velocity time, distance time, position time, or acceleration versus time. And it's one of the ways that you should be able to describe motion with graphs, with words, any of those. Okay, so I'm going to say this again. This is not about memorization, right? There are things you can memorize and there's things that you can't memorize. What I'm looking for you is for you to interpret, right? To apply the stuff that you memorize, definitions, laws, ideas, things like that, and then apply it to every new situation. So there are things you have to do before you can even begin to answer a question regarding a graph, whether you're drawing the graph or you are interpreting a graph that's provided for you. So there's 4 things I want you to do. First, you have to look at the axes. I know that might seem really obvious, but I can't tell you how many times people make mistakes because they didn't look closely at what is actually on the x and what is actually on the y-axis. So that's something that I want to stress to you is really important. Second, make sure you remember and can easily recall what those variables are. If there's time, okay, we know what time is, but what's on that y-axis? In this particular cases, we're going to be talking about displacement, position, velocity, speed, acceleration, all those kinematics terms. You have to know what those words mean and really understand their significance. Okay, step 3, you're going to interpret the slope using the slope formula. And 4, you're going to see if the area has any meaning. So you have to know how to find the area under a curve. Okay, only after you do those things do you even want to begin to answer a question. Now, at first, when you do this, it's going to take a lot of time to do each question. But those things should become more and more automatic so that you can get to answering the question a lot quicker than you might have when you first start. So be patient with yourself. So I'm going to show you a few examples. I don't want you to memorize these. These are just examples to show you the steps. All right, so here's the 3 steps I already went through. So let's do it for this particular graph. So first look at the axes. This is an x and this is t. X stands for position. This is where it is. So I can see it's at 0 here and the number, like the position is getting bigger and bigger over time, right? I know that position is where something is relative to the origin. So origin is where position is 0 and then we're going in the positive direction, right? We're getting bigger and bigger values. So that's interpretation, right? So step 3, so we're looking at the slope, delta y over delta x. So that means it's delta x, right? Position, change in position over change in time. Well, I know that change in position over change in time is velocity in physics. So if I know that, then if I know the slope, I know the velocity. The area would be this area here, area of a triangle, which is 1/2 times x over t. Well, that doesn't have any meaning in physics, right? The position times time doesn't mean anything. So that's not useful here. So then what conclusions can I draw? Well, I can say the position is getting bigger and bigger as I go away from the origin, right? I'm moving forwards. And the slope is constant, therefore velocity is constant. So whatever I could say about the slope, I can say about velocity, right? That's what we were saying here. Velocity is delta x over delta t, therefore slope is velocity. So that's how you put that together. Now go answer some questions about it. I mean, we're not going to do that part now, but that's how you think it through. So let's say you had a velocity time graph. So here's the velocity time graph. Here are those first 4 steps. First, I'm looking to see on the y is velocity, on the x is time. Velocity is the rate of change of position, how fast position is changing, how fast the object is moving, right? I know that slope, right, would be delta v, right, the y, over delta t. Delta v over delta t is acceleration. That's the definition in physics. So I know the slope of this graph is acceleration. Then the area under the curve, right, this area here, that I'm boxing in, this area would be height times length times height, so it would be time times velocity. So this velocity times time, that's displacement. right? If I took average velocity equals change in d over change in t and rearrange that, I'd get v times delta t is displacement. So I know area of this graph is displacement. So all this stuff is going to be in your head as you think it through. I would jot it down in the margins of your paper or whatever as you're thinking. And then you can draw some conclusions. Well, if the velocity isn't changing, right? Because I have some value here and it's always the same all the way across. Therefore, it's constant velocity. We also know that it's a positive velocity, so I know that's a positive direction, because I know that signs in physics, right, when positive vectors, right, means positive direction. The slope is 0, therefore acceleration is 0, right, because the slope is acceleration. The area is positive, right, I would get velocity times time would give me some positive number, so it's got a positive displacement. Well, I already said that, right? I have that 2 different ways, but that's good to know too. All right, so let's look at another one. Here's an acceleration time graph. So you can do the same thing. The axes have acceleration on the y. Acceleration is how fast the velocity changes. Here's time here. Slope would be change in acceleration over the change in time. That has no physics meaning. This area here would be acceleration times time. Acceleration times time is the change in velocity, right? Because a equals delta v over delta t, multiply both sides by delta t, you get a times delta t is your change in velocity. So the area is change in velocity. So that's a lot of good information off this graph. And so now I can say, okay, acceleration is not changing. It's a constant value. It's a positive value. I don't know if that means increasing or decreasing because no information is given about the velocity itself. The area is some positive number, so I know it has a positive change in velocity, but again, until I know either my initial or my final velocity, it's not enough information to do anything with. But it would depend on what the rest of the problem said. So what follow are a bunch of, like 3 more questions, one with a position time graph, one velocity time, one acceleration time, and the solutions follow. So what I'm going to do is here's like the graph, and you can kind of fill in the blanks here if you like in your notes, and then and you can pause it, and I'm going to then show the answer, and then I'll show the next slide with the interpretation. You fill in the blanks, pause it while you do that, and then the next slide has the answer, and so on. So just when you get to the question slide, pause the video, and then you can check your answers after. Okay? So I'm just going to go through these, so pause as needed.